Investigate how paper chromatography can be used to separate and tell the difference between coloured substances. Students should calculate RF values. So you've probably done chromatography throughout your kind of school career, and this one will be slightly different to the ones you've had, because this time we're going to be using 4 bits of chromatography. We've got a B, a C, a D, and then when I find the A, we'll have the A. There we are. Okay, now we've also got something we've labelled U. That U, okay, is an unknown solution. I don't know what's in there. So I've got these 5 inks, okay? A, B, C, D, and then U. I know that these 4 are pure substances. That means they only contain 1 ink. U, I know, is a mixture, but I don't know what inks U contains, okay? So, you'll need your chromatography paper, your inks, you'll need a beaker, and you'll need some water. I've just poured some water in a jug here. Now the trick with chromatography is to make sure the water isn't too high. You want this chromatography paper to just touch the water, okay? You will also need these. Now these are called capillary tubes, and you've got to be very careful with them, okay? Because they are made of glass and they can break very easily. So, we've got our chromatography paper, we've got our inks, we've got our capillary tubes. The other thing we will need is a ruler and a pencil. Okay? The reason we're using pencil is because pencil does not dissolve in water, whereas these inks we know do. So roughly about 2 centimetres up on the chromatography paper, and I'm just going to make a little mark, you want to be drawing a line. Something like that. I'm going to do the same on the other chromatography paper because I'm going to use 2 today, just so I can fit all the inks on and they won't run into each other. But if you have a bigger chromatography paper, you could put them all on 1. So, there you are. I also will be putting an X on them as well. So I'm going to do 3 on the first chromatography paper and only 2 on the next chromatography paper. Now you don't want these X's too close to the edge because otherwise it won't work as well. So on this I'm going to have A, B, C, and on this one I'm going to have D and then the unknown, which we've called U, okay? So I've got these chromatography papers which I've labelled. So we've got the 5 inks there, A, B, C, D. Those are all pure. The unknown is the mixture. So taking a capillary tube, which is a glass tube, being very careful, and opening A, you dab the capillary tube into the inks, and you'll notice it will take up some of the ink, okay, through this capillary action. Just putting the lid back on, okay. All you have to do is pretty much dab the ink on the cross with A. Now I clearly can't use this capillary tube again because that is a pure substance and I don't want to mix it up. So I'm going to place it into a used tube beaker. I'm going to do the same for B. And then finally, this unknown solution. Now we don't know what this is made of. So this is the one we're testing for. So notice it looks kind of black and dab it on. Okay. Again, putting it in the used capillary tubes. Now, we've got all of the chromatography looking how it should. We're going to put them in water. Okay? Now, it depends how deep your water is, but this is the important bit. The water, or whatever liquid you're going to use, the solvent, which in this case is water, should not go too high up the chromatography paper. Should only be slightly on it. If it does, the inks will run into the water and they won't move up the paper. So I'm just going to do A and B and C first. You put it just in there. Now, as you're putting it in there, I tend to fold it over. Now, on the AQA specification, it says for you to use a glass rod across the top. Again, you could also use a pencil, you could wrap it round both. But then notice the water is travelling up the paper. Okay? I'm also going to do the same for the next one, filling it with a small amount of water, again not too much, and putting D and U in. You should see something happen. Ideally, we would wait for this solvent front, this line where the solvent is up to reach 3/4 of the page. However, on this one, we've noticed a slight contamination. And I would guess it's because when I was doing it, a small drop of ink dropped roughly on there on the page. And in fact, I would be pretty certain that it's actually the unknown that I've accidentally dropped on it because it's split into 3. So we've got A here, B, C, D, and then the unknown. I'm going to ignore this drop. And contaminations can occur, and you've just got to be extra careful when doing it. That was probably my mistake, but because of my mistake, we should really repeat the whole experiment.
So, minus the contamination, I'm going to show you how to calculate RF values. Now, this is the second part of your experiment and how we compare the movement of different solvents. This is a ratio of how much the solvent has moved up your chromatography paper compared to how far the ink has moved up. So very important, while it's still wet, you need to do a pencil line to show just how far your solvent has travelled. So I can just about see that my solvent, my water, has travelled this far. Now that we have the distance that our solvent has travelled, I'm going to leave this to dry thoroughly so that I do not affect the results. Once dry, I'm going to measure the distance between my 2 pencil lines, and that will tell me the distance that my solvent has travelled. So I can see clearly here that this is 5.4 centimetres. So my solvent has travelled 5.4 centimetres, or we could say 54 millimetres. Once I've marked the solvent distance, I'm also going to do a very faint pencil line to show the distance that my substance has travelled. Now I'm going to measure from the very top of where it has travelled. These two distances we're going to express as a ratio. Now, when you've calculated your RF value, your number should not be more than 1. If you have an RF value of 1, this would mean your substance has travelled as far as the solvent has travelled as well. So the equation you're going to need to know, the distance that your substance has travelled divided by the distance that the solvent has travelled. And that's going to tell me my RF value. So, in my example here, My substance has travelled 45 millimetres. So I'm looking at substance A. So A has travelled 45 millimetres. So to calculate the RF value for A, we will do 45 divided by 54, which gives us about 0.83 recurring. One thing to note, make sure you are using the same measurement, the same unit for each of your measurements. Okay, so 54 millimetres, 45 millimetres. Now, this number is smaller than 1, so the substance did not quite travel as far as the solvent did. Each of our pigments here will have a different RF value and a different colour. We can use those RF values to calculate which one, or to work out which one of our inks is in our unknown mixture of inks. So in our example here, both A and D have a slightly pinkish colour. However, they will both have different RF values that we can compare to see which one of our pigments, which one of our colours is the one in our unknown mixture. So here we have calculated, using this formula, the different RF values for the different dots. Now, for my values of U, I can see there's clearly 3 distinct colours. In an exam, they would have 3 distinct blobs or 3 distinct patches because the exams are printed in black and white. The same principle applies here. So I've measured the RF value for each of those 3 distinct colours, those 3 distinct patches. I can compare these numbers to the numbers that I've calculated for my pure inks. Now, A and D were both a pinkish colour. However, the RF value for D was 0.6. One of my RF values for U, for the pink patch, was also 0.6. In comparing those, I can determine that they are quite likely the same ink. My value for B is 1. Now, 1 means it has travelled as far as the solvent has travelled as well. So my value is 1. Again, my mixture of inks also has a value of 1. The yellow patch in the middle came out to 0.9. Again, 0.9. U has been a mixture of B, C, and D.